In this lecture, we're going to talk about input and output. That is, how do we get data in and out of a machine, and what sort of things are we attached, and how are they attached? So we're going to start out today, and we're going to first talk about a bunch of different I/O devices and the performance. We're going to talk about the different sorts of buses you find in computers, and we're going to talk a little about latency and throughput, and how those are different. We're then going to talk about how you connect devices to your computer. So we're going to talk about buses and serial connections. Then going to go on to talk about how you talk to the I/O devices. That is, how are we going to send data back and forth to them? We're going to cover three different ways of doing this: I/O instructions, memory mapped, and DMA, that's direct memory access. And we're going to discuss when you talk to devices. So are you polling for data, or do you get an interrupt when data is ready? And finally, we're going to go over an example, which is how Ethernet works. So let's get started with I/O devices and performance. So let's take a look at the sort of I/O devices you find today. So in a machine, we have disks and keyboard and cameras and networks and displays. These are the regular things that you have hooked up to your computer today. And for interfaces, we have a whole bunch of different standards. There's USB, which everyone's familiar for plugging things externally. PCIe is what we use internally for hooking up things like graphics cards. SATA is used for disks. Ethernet and wireless 802.11 are used for networking. And then we have a bunch of other connections for audio, video, and the like. So lots of different connections inside the computer. Let's take a look at some of the speeds that these technologies provide. So here we can see across those different technologies the sort of data transfer speeds that they provide. And there's some interesting things to note here. We'll see, first of all, that wireless is by far the slowest of all of these. And the reason it's so slow is that it's just much harder to send data over a radio than it is to send it over a wire. You can also notice on the other extent that internal devices are the fastest. So PCIe is inside the machine, and it is far faster than any of these other standards. And the reason for that is it has very short wires because it's inside the computer, so you can make those wires go very quickly. So now let's take a look at different storage technologies and their speeds and costs. So here we're looking at technologies from tape, hard disks, non-volatile RAM, that is flash, DRAM, and SRAM. And you'll see I've got two SRAMs here. One's 8 megabytes and the other's 32 kilobytes. So these two different SRAMs are, one is for a very fast SRAM and the other's for a larger SRAM. And if you look at the capacities, you can see there's a huge range here. Disks go up to 3 terabytes, whereas DRAM only gets up to about 16 gigabytes per module. You can see that this is going to affect where you use these devices. If we take a look at latency, we see again a huge range of latencies. So tape can take anywhere from 10 to hundreds of seconds to access data because it has to physically fast forward or rewind the tape. Disks, on the other hand, are far faster. It takes 8 milliseconds to access data on a disk, but this is still really slow if you compare it to DRAM or SRAM, which are down in the nanosecond range. And the reason for this is that disks have to spin a physical metal piece of material and spin that around to get to the data they want, whereas DRAM and SRAM just have to access it electrically. The throughput for these devices also varies enormously. Tape, even though it has a much higher latency, has a throughput that's fairly comparable to disks. You can still read lots of data in a row, it just takes you a long time to find a specific piece of data. You can see here that non-volatile memories, NVRAM or flash, are much faster than disk, but far slower than DRAM and SRAM. And so if you just look at this data here, you'd say, well, we should build everything using SRAM or DRAM because it's far faster. Then you go over here and you look at cost. And you see that SRAM costs thousands of dollars per gigabyte, whereas DRAM's only a few, and flash and disk are far, far cheaper. And so what you see from this is that we're going to have different types of storage that we use at different places because of the different costs and throughputs. So what was this NVRAM I've been talking about? This is non-volatile random access memory. This is like flash memory. It's memory that retains the data when you turn off the power. So looking at this data, why would anyone ever use tape? Well, the answer is it lasts longer. So data on hard disks is only good for 3 to 5 years, and then you basically expect the hard disk to die. Tape can last 10 to 20 years, so it's used for archiving. Lots of companies are required to keep data records for a long time for legal reasons, and they use tape for archiving. However, disks are so much faster and just about as cheap So there are lots of companies which are trying to use disks for archiving, and they use clever software and hardware solutions to try and make sure the data is good even for many years. Now let's discuss a little bit how hard disks work. So this is what you find inside the hard disk, and you basically have a platter. This is a metal platter that spins, generally pretty quickly, and the data is written on this platter. In most hard disks, you'll have many of these platters put together to increase the amount of storage. You also have a read-write head. This is a device which physically moves back and forth across the platter to access the data. If you've heard hard disks making sort of clicking noises, that's the sound of that head zooming back and forth. The data in the hard disk is stored in tracks or rings around the disk. Each of these tracks is divided up into sectors, where a sector is 512 or 4096 bytes. Now the performance of the hard disk is determined by two things. So the first is the rotational latency, and that's how long it takes the disk to rotate around to get the data under the read head. So if I have data at this point on the disk, how long is it going to take for the hard disk to rotate around so that that data is under the read and write head? The other is seek time, and seek time is how long it takes the head to move to the right track. So this head is going to have to physically move on the disk in order to access that data. And the combination of rotational latency and seek time gives you the average latency for accessing the disk. So let's take a look at disks and let's discuss some things you might care about for using a disk. So if you're doing high performance computing, that is you have a supercomputer that's processing large matrices or large sets of data, or if you're doing media processing, so you're compressing video or processing audio, what you care about is throughput. You care about how much data you can get through per second. It doesn't matter how fast you get to the data, I just need to get lots of it so that I can go through it. If you're dealing with databases and web, you care about latency. That is the time to get the first part of data. So if I'm logging into Facebook, I don't care how quickly Facebook can load 1,000 users. I care how quickly it can load just my account. If you're running on a desktop machine, well, it's somewhat of a mixture. Some things you do, you want them to be very low latency, and others are high throughput. How about a cell phone? What's the right thing to optimize on a cell phone? So the reason we're talking about this is different media have very different behavior. So here's the performance of a disk. And what you can see from the disk is that it's doing sequential reads and writes. That is, it's reading and writing lots of data in a row. It runs very fast, almost 200 megabytes per second. But if it's doing random reads or writes, that is jumping all over the place to get just one small piece of data, it's far, far slower. It's because it has a much higher latency. We also notice that the performance on the disk varies depending on where you are. Some places on the disk, the performance is half as fast as it is in others. So if you look at this disk, you can see that it's about 300 times slower for small random pieces of data than sequential ones. So hard disks are very good for applications where you care about throughput, not so good when you care about latency. Now we've seen stuff that is good for latency. So we've seen that non-volatile memory, flash, has much lower latency. DRAM has much lower latency, but it's much more expensive. So the question is, can we take these technologies and can we combine them together to get the best of all of them? And the answer here is yes, on average, but not all the time. So we can use hard disks for their large capacity, because they're cheap. We can use flash or non-volatile memory for sort of a medium capacity and very low latency. And then we can use DRAM to keep very few little bits of information, because it's so much more expensive, but at a far lower latency. And if we combine all of these together, what we can do is we can get something that on average has the best properties of all of these. That is, it has on average a lot of capacity and low latency. Let's take a look at how that works out. So here's a graph for a storage system. And what it shows the time the storage system is running, and then it shows the latency. So dark blue indicates that there's a lot of accesses at that latency. And what you can see here is this is the performance of the hard disks. Their latency isn't very good. They have a latency that goes up to 10 milliseconds for accessing the data, and that's not surprising because we saw how hard disks are slow. What you also see here is a small amount of accesses that have very, very low latency. And these are the accesses that are hitting in the DRAM cache. So the server running this has a lot of memory, and it's using that memory to store recently used data so it doesn't have to access the cache. And as you can see, this is reducing the latency on average. Now, what if we add flash or non-volatile memory to that? Well, here we've turned on non-volatile memory or flash. And what you see is that flash has a latency that's higher than DRAM, but lower than the hard disk. And so what we get here is we get better average latency because now some of that access is in flash, and the flash has lower latency overall. We can't put all of our accesses into flash because it's too expensive to have that much flash. So with lots of disk, some flash, and a little bit of DRAM, we can get on average a high capacity and a low latency. So what's been happening to storage prices over the years? So here's a graph of them, and we can see what's happened to disk. Its price has gone down significantly, DRAM's price has gone down significantly, and flash has gone down significantly. Flash, as you can see, is a much newer technology, so it hasn't been around as much. But if we look at this data, even though things are getting cheaper and cheaper, we can still see that DRAM is 10 times more expensive than flash, and flash is still 100 times more expensive than disk. So we're not about to replace everything with flash anytime soon. So what problems do we have with flash? The biggest problem with flash today is you have to write data in large chunks. So we've got 4096 bits at a time. That means if I want to update 1 byte in my flash memory, I have to read and write 4096 bits. This is also a problem because flash wears out quickly. So when you read and write flash many times, you actually damage the cells that are storing the data. So we need to intelligently choose where to write. We need algorithms that spread out the writes to increase the lifetime, and we need a lot of spare blocks in our flash so that if we detect a block that isn't working anymore, we can swap in a new one. The biggest problem, however, is that flash is expensive, but it's getting a lot cheaper. So what are the benefits of flash? Well, it's far faster. We saw the throughput is much greater than a hard disk, and it has enormously lower latency. Flash latency is in the order of microseconds versus milliseconds for hard disks. And the real big one here is that it's lower power and heat. In a hard disk, you're spinning a piece of metal, which generates a lot of heat. So flash is much better here. And the conclusion here is that non-volatile memory, or flash, is going to take over the world. Hard disks are going to go away, and everything's going to be stored on flash, but that's not going to happen until it's cheap enough. The other thing that's important to point out here is it may not be flash as we know it today. There are a bunch of other non-volatile memory technologies, such as phase change memories, magneto memories, that may win out in the long run. It's not clear which ones of these are going to be the ones that take over, but it's pretty clear that we're going to move everything to solid-state memory.